lecture. Professor McGeer was appointed Regius Professor of Engineering at the University of Edinburgh in 1982. He has held appointments at the University of Queensland, Australia, Leicester University, UK, and Strathclyde University. He is the author of several books, including his latest edition entitled Engineering Human Joint Replants in 2013. His lecture this evening is entitled Engineering the Future. Tantalizingly, there is no comma in the title, so I am anxious to hear what Professor McGeer has to say. Joe.
Thank you very much, Professor Whalley, for that very kind invitation, and I'm honoured and delighted to be here in Dubai, and especially here at the British University in Dubai. Engineering the future, and no comma deliberately, because you and I, between us, are engineering the future, not only of me in the United Kingdom, in Scotland, but as I look around there, you people are engineering the future for Dubai. And I want to explain why I think the future of your country very much rests with you. Here we are, two quite different types of university in different parts of the world, in different continents. Here we have the British University in Dubai, set up, inspired by a ruler, the Sheikh, with vision of how he should see Dubai developing, where young people are very much the future. And interesting enough, set it up as a research university where creativity as well as hard work will mark the future of where Dubai will go. And linking up with an ancient university back in Scotland, founded in 1582, more than 400 years ago. And my appointment at Edinburgh coincided with its installation, celebrations marking 400 years. But there's a difference between your university and Edinburgh University in that it took from 1582 to the 19th century for Edinburgh University to get round and establish engineering. When it was set up, Edinburgh University concentrated on law, in theology, and medicine. And Professor Whalley and his colleagues and I were just recounting yesterday, in those days medicine was actually, and medicine at Edinburgh is probably its most preeminent faculty. But because anatomy was unknown, there were two characters in Edinburgh called Burke and Hare, and they used to go and rob graves, and then they would bring corpses to the professors in the university in order to practice practice anatomy, until they were caught. and there were sentences whereby they could never do it again. But why did it take Edinburgh University all that time? And why were they called Regius Professors? Well, the 19th century saw an industrial revolution in the United Kingdom. Another Scot called James Watt found that you could power using steam, and he depended on coal to fire steam engines. And that was the start of a railway industry in the United Kingdom, where trains could go from London up to Edinburgh, really right up to the north of Scotland. And two people who pioneered railway engineering in the United Kingdom, they were called Stevenson, and they lived in Newcastle. And the older Stevenson sent his son to study at the University of Edinburgh. And when he arrived there, he was found he could be offered tuition in physics and chemistry and mathematics. And he said, "Where's the engineering?" And they said, "Well, we don't do engineering here." And the professors of physics and chemistry went to the government of the day and said, "We think you should establish engineering as a new discipline, where these people can get the basic training in physics and chemistry and mathematics, but we think we should now be able to teach them engineering." The government of the day took it to the reigning monarch, who was a queen, Queen Victoria, and she gave an order to establish what was called the Regius Chair of Engineering, the Regius Professor of Engineering. And that title and that position exists to today. And in those days, the government or the Queen paid half the salary of the Regius Professor, and the university found the rest of the money for his salary from teaching. And in my home, I'm the proud possessor of a manuscript signed by Queen Victoria's successor, Queen Elizabeth II. And she has signed this document appointing me as Edinburgh University's Regius Professor of Engineering. And those titles exist today. And there are only 3 Regius Professors of Engineering in the United Kingdom. One in Cambridge, one in Glasgow University, and one in Edinburgh. So there we are. You all want to be engineers. That's why you're here. And let me just remind you of one or two people. When I was young, I watched a flickering TV one night, and it was showing the first man to step foot on the moon. And in the UK, it was about 3 o'clock or 4 o'clock in the morning. And I saw these shaky TV pictures in black and white of a man called Neil Armstrong climbing very carefully down steps from a spacecraft and setting foot on the moon. Incidentally, Neil Armstrong, you might not know this, but his grandfather was actually Scottish. And there's a plaque down on the borders, quite near to Edinburgh, commemorating that Neil Armstrong, after he had stepped foot on the moon, came and visited the hometown of his grandfather. Here's something that's very much British-oriented. Christopher Cockerell was the man who he built boats down on the south coast of England, and he thought of a way of actually using air in order to raise up a craft and push the craft just over the surface of the water. And it was hugely successful. Patents were taken out, and it made Cockerell a man who just was an ordinary guy building boats to a new industry. And here's somebody else that you probably have never heard of. Williamson, somebody called Theo Williamson, one of these unsung heroes. And at the age of 22, he wrote an article in a magazine called Wireless World. My father was an electrician. He had this kind of vision that his children should go to university. So I went to university, and my brothers and sister went to university as well. But my father used to read Wireless World, and it showed all these, and my father used to play with radio and built the first crystal set for his father and mother in a small town called Bothwell in Scotland. But Williamson published this idea of an amplifier, and he got the idea because his father used to buy this magazine in their home in Edinburgh. And if any of you actually come to Edinburgh, get in touch with me, and I'll take you to a house where there's this plaque which commemorates that Williamson lived in this flat, in this house. His father was a great do-it-yourself man. He ran a car hire business. This was the day before central heating, but his father put anthracite stoves into every room in the house. And Williamson said years later that it was the best heated house in Edinburgh. The reason why Williamson was actually able to do this magazine was that the war had broken out, and it was discovered, and Williamson had to go and do military service, and they found out that he had had TB as a child, and this disqualified him from military service. He applied to do research in the government of the day in the UK's laboratories, and he was interviewed by a man who said to him, "I can smell a research scientist and engineer a mile away, and you're not one of them." So Williamson was turned down for the forces, turned down for scientific research through the war, and was then, because of that, in the 70s, they said, "You're a total failure." And he was sent to London during the Blitz to work in a factory where his job was testing valves for aircraft. And you'll find this as you go on. A good boss here in the British University, good professors, and they see your potential too. He had a good boss, and he saw, his boss was called Graham Woodville. Several years ago, actually, I went to see Woodville to find out, and he said yes. He said Williamson was totally bored testing valves. He put a valve in, if it lit, it worked, and then it was put into a box and sent off. And he said, "Have you any ideas of what else you'd like to do?" He says, "I've got an idea for an amplifier." He said, what are you going to do with your amplifier? He said, "Well, I think I can improve the quality of sound." So Woodville, his boss, said to him, "Okay, if you've got 500 valves to test today, or 750, you test them, and then the rest of the day is yourself, and you go on with designing your amplifier." So Williamson designed this amplifier, and I've seen the amplifier, and I've played music through it, but the effect of that amplifier was to improve the quality of sound that came from gramophone records. No end. He never made a penny from it, and he published the design in a magazine called Wireless World. After the war was ended, here's why these three people are important. Each of them, in his different way, had studied engineering. Armstrong did aeronautical engineering at Purdue University in the United States. Apparently and then he joined the American Air Force. Apparently a very kind of calm person, totally unflappable. And Cockerell, interesting enough, the course that you're interested in here is systems engineering. But Cockerell first of all studied mechanical engineering, and then they went on to study radio and electronics. This combination of mechanical and electrical engineering. And Williamson, he went to Edinburgh University, and he studied engineering as well. If that's not convincing enough, what about thinking about Paul Dirac? Dirac's a French name, his father was French. And Paul Dirac studied electrical engineering at Bristol University. Later on, he went into the realms of theoretical physics, and he got the Nobel Prize for quantum mechanics. And that quantum mechanics is the basis today of what we now know as nanoengineering. The capacity for parts that are so small that they're beyond the capacity of the human eye. And we owe that to somebody who had studied engineering as a first discipline, just like you. And here's a rather unusual example. Robert Louis Stevenson. His family built lighthouses, and if you ever come to Scotland, round the coast of Scotland, you'll see lighthouses built by the Williamson family. And the father in the family sent Robert Louis Stevenson to study engineering first of all, and then law at Edinburgh University. He became acquainted with the first Regius professor and wrote a book about him. We well know that Robert Louis Stevenson became much more famous, not for his engineering, but for writing books like Treasure Island and Kidnapped. And he used to come and visit his grandfather, who lived out in the same district of Edinburgh that I did. And he wrote a poem there called The Swing, and there's now a swing cafe remembering where Robert Louis and Stevenson used to come. But the reason why I introduced that is communication. And we as engineers, not only are we expected to do the work, but we're expected to be able to communicate it too. And one of the best examples of communicators in the written word was Robert Louis Stevenson. What did Williamson? So back to Williamson. Here's Williamson being capped in Edinburgh. And Williamson studied mechanical engineering, electrical engineering. He realized the benefit of electromechanical systems, and he realized the importance of mathematics and mathematical type subjects. And that is the basis of systems engineering as taught here in the British University in Dubai. And that was a man who realized 60, 70 years ago of the benefit of combining electrical and mechanical engineering. And you know yourselves that any mechanical engineering device, whether it's a motor car or a train or any form, it's the electrical engineering within it that is often the thing that actually makes things go. After the war, Williamson came up to join a big electrical mechanical company in Edinburgh called Ferranti. Still exists today. And that's the headquarters of Ferranti. It's now called, through, as always, international companies would take them over. Still exists today. It's now called Celex. But that's where Williamson came. He came back to Edinburgh. And his boss of the day had a problem. The boss found that the machine tools that existed in Ferranti were not able to turn out parts either accurately enough or fast enough to meet up with the orders that were needed from Ferranti. And he sent for Williamson as a young guy in his 20s, just like you. And he said to him, I've got a problem here. Our existing machines can't make these parts fast enough or accurately enough. Go away and solve them. And William said, well, how am I going to do it? And his boss had trained as an engineer, and then had gone into management, just like some of the people here. He said, I don't know how you're going to solve it either, but all I know is you are at the peak of your creative career. Go and get 2 or 3 of your friends together and work together and come back to me with a solution. That was all. So Williamson went away and he got 2 or 3 of his friends together and they made a little group and they did brainstorming. And they brainstormed and they came up with an idea of using computers. The computers to drive a tool in order to cut out a shape. And bear in mind, this was before computers as we know them today. This was very much the early stage, very much where computers would fill this room. And here's this young guy in his early 20s saying to his boss, we think you should use computers to cut out these shapes. And the shapes were made of aluminium, and they were for radar systems to put into aircraft. And the boss says, are you serious? Tootle said, are you serious? He says, yes. He said, well, go ahead and make a machine to demonstrate to me. I just don't want your ideas. Go ahead, you make a machine to tell me that this will actually work. So Williamson and his friends, they put together a machine and they proved to the boss that they had found a solution where no solution in engineering had been found before. And these components were cut out fast enough and accurately enough to solve Ferrante's problems. I don't know what the problem will be in 10 or 20 years' time, but all I can tell you is one of your bosses will come to you and tell you, I've got a problem here and I need a solution. And you'll be sent away in order to figure out what the solution should be. Ferrante went into the business not only of making parts for radar, but they went into the business of making machines that would actually cut out these parts. And who best to be an ambassador for Ferrante was Williamson himself. And they sent Williamson all over the world selling Ferrante machines using computer control. And Williamson said that he would go into a factory, whether in the United States or Germany or Japan, and people say, DTN Williamson, you're not the same DTN Williamson who published the Amplifier in Wireless World. And Williamson, and he was a very modest man, would say, yes, I'm the same Williamson. And Williamson said it opened up doors where previously the doors were closed because he designed this amplifier, and all these people were hi-fi enthusiasts. And they were building their amplifiers because he had published how to publish it. No, even in the district of Collinton where I live. One of my neighbours said he had built a Williamson amplifier. And a friend of mine, a colleague at the University of Tokyo, also said he had built an amplifier based on Williamson's design. So it shows you, amplifier to building a machine to cut out parts. And it was the creativity and the benefit of Williamson's university education that it paid off. Ferrante took out patents to protect the work, as any good company would do. And after that, they said, okay, you can go and start talking about this work around the country. So Williamson ended up talking about his Ferrante computer machines. We in the UK, and again, I'm encouraged by the fact that the big engineering institutions in the UK, they determine what we can teach in universities. One of them is now the Institution of Engineering and Technology. And they absorbed this institution called the Institution of Production Engineers and into their midst. And Williamson went down to talk about this new revolution that he had discovered, developed and invented at Ferranti. And what he didn't know was within the audience there was a man called Mollins sitting. And Mollins owned a factory in London. The factory made machines to make that made cigarettes. They didn't make cigarettes themselves, but they manufactured machines that could make cigarettes. And you know yourself in those days, well, smoking is now not so popular, but in those days everybody smoked. My father smoked a pipe, but everybody, most people, if you saw the old movies from those years, everybody was smoking cigarettes. A very kind of chic thing to do. But Mollins listened to what Williamson was telling the audience about. And after the conference, he approached Williamson to say that his factory in London, the equipment in it, the machines in it were so antiquated, and because of the orders for cigarette making machines all over the world, they were not able to make the machinery fast enough. And would Williamson be interested in joining Mollins? It was said that the salaries that Ferranti paid were so low that Williamson used to breed chickens at home. And he would come in at the start of a week and say, "Who would like chicken for your weekend lunch?" And people would say, "Well, I'll have a chicken." So by the time Friday came, of course that's the end of the week in the UK, if people had bought 3 chickens, Williamson would come in with 3 dead chickens, and he would sell the chickens to his friends and pocket the money to augment his salary at Ferranti. Legend. What Williamson did, what Williamson was offered by Mollins, was 4 times the salary that Ferranti were offering. But this time they had 4 children. And it was also more than the salary of the British Prime Minister. So on the basis of that, Williamson had integrity. And he went and told the managing director of Ferranti, not wanting more money, but to tell him what he had been offered. And Tootle, the man who had been saved by Williamson's work, said to him, "Look, I think this is an opportunity for you. In no way can Ferranti pay you that kind of money, you know. We couldn't offer twice. I think you should think very carefully. This is a decision for you and your wife to make. But we think you should think about it, and if necessary, just go. And you go with our best wishes to make a success of it." So Williamson left, and he went back to London, this time with a wife and family. His ideas for Mollins were actually much more ambitious. He was now inspired that he not only could just build a machine using computers to cut out shapes. He said, why couldn't you just have a computer to do absolutely everything? Do absolutely everything. And right at the bottom there is the basis of what Williamson envisaged. We all do online shopping. My wife has come for the first time to Dubai with me. And before she came, she went online. She said, "I think I might try and get a new dress because of the weather." So she went online and she saw this outfit and she ordered it online and it was delivered to her house. But he saw that for an entire factory where the whole factory was under computer control. You would order the components by computer. You would store them using robots. And then you would have machines to make the machines. And then it would be taken from the factory to lorries. And even the accounts would be monitored by computer. Total visionary. And Mullins said, let's go for it. And Mullins was he was a businessman, but he saw this was actually really a total revolution in how industry could work. And other industries as well realized that this system could be applied, in particular in the United Kingdom and Japan and the United States and Germany. Cars started to be manufactured by the use of robots that Williamson had envisaged for this little factory in London called Mullins. The greatest accolade that, and it's usually reserved very much for scientists. Engineers are few and far between, but Professor William was me and I just talking today, but one of his colleagues that was made a Fellow of the Royal Society of London. And the members, and this was established round about the time that Edinburgh University was established, and one of the early Fellows of the Royal Society was Isaac Newton, who, you know, the famous dropped an apple and he realized that gravity. So one of the senior members of the Royal Society of London was sent out to Mullins' factory to see if it was true what was being said about this man called Williamson. And they said it's true what this man has actually done. And Williamson's name went forward, and in the first year, and usually these nominees stay on the books for years, he was elected in his first year of nomination, and he was given the greatest accolade that a scientist and engineer can have in the United Kingdom. And his wife said that he regarded this as a real testimony. And you remember what I said earlier, when he applied to join the Scientific Research Establishment during World War II in the UK, he was turned down because he wasn't a research engineer. Because of that, the body that supports research in the universities in the UK, it's gone through it's now called the Engineering and Physical Science Research Council. And at that time, it was called the Science Research Council. But they came to Williamson. He still had his job with Mullins, as he was now director of research. And they said, would you consider becoming the director, chairman of engineering? Because we think your vision of what is going on, what you've done, is what we need, where we're pumping public money into where the future of the UK should be, just as your country is pumping in money in order to see where the future of your country should be in terms of engineering. So Williamson agreed, and he became the chairman of engineering. Meantime, what was I doing? I had done a bachelor's degree, and my final year, just as I was graduating, I'd actually been an athlete. You wouldn't think so now, but I usually do a lot of running. I'd have been near graduation. I was offered a couple of jobs in the industry. I'd have missed total year of competitive athletics. And I was out on a training run with a friend of mine who'd graduated the year before, and he said, what are you going to do? I said, we're offered a couple of jobs in the industry. He said, are you going to take them? I said, well, I'm very interested. He said, the Professor of Mechanical Engineering is looking for people to do research. He said, why don't you come down and talk to him? And I thought, well, do I really want to be doing this? And I remember saying, is it relevant to the needs of industry? He said, very much so. So I went down and I thought, well, if I do this, I can get back and start doing some more competitive athletics. So I knew the Commonwealth Games, a kind of British type thing, big international. I knew the Commonwealth Games were coming up. I thought, gosh, if I go back in training, I might even get into represent Scotland. So I went down to see the Professor of Mechanical Engineering, who had come from a shipbuilding family in Glasgow. And he told me what was needed. And it was the end of the week, and he said, I don't want you to decide now. I want you to go away and think about it and come back in and tell me on Monday. Go and talk to your family, go and talk to your friends. And so that's what I did. Didn't put any pressure on me. And I went in and I started doing research for the aircraft engine industry, dealing with putting tiny holes in cooling blades, in cooling holes. And I decided just to bring one. This is just a small version. But I noticed over on the right-hand side, Rolls-Royce are one of the competitors. And over my working life, and I'm still doing work with Rolls-Royce today, putting tiny holes into cooling holes into turbine blades. And the great thing about that was this isn't a seminar on electrochemical machining, but basically it let me drill tiny holes without any tool wear, even in the hardest of metals made of titanium or nickel-based alloys or stainless steel. And I was enjoying it, until Williamson came along. And I went to a meeting where, remember, Williamson was now the chairman of engineering for the Science Research Council. And he had had reports that the die and mold industry, this capacity, now look at this is made of plastic. And I can tell you that just looking at it, looking at the indents in it, the mold for that was made by a process called spark corrosion. That's the kind of trade name, electrodischarge machining. This was something actually I was working on. And that's new technology. Before that process was used, in the UK, the people who made molds and dies were fathers and sons. It was manual skills. The father would learn how to do it from his father, and his son would come into the factory and he would show his son. And so it was passed on, this tradition. And Williamson was told that the number of workers who had these skills was diminishing. And he said, well, we need new technology in order to do this. And a call was put out for people who had skills and new methods of machining in order to take the skill and put it into modern methods. And I found myself involved in a program where the main universities in the UK became partners. And here they are. We were now making molds by one process, and we're finishing it off using the same. And we're doing it much more quickly. And there was a representative who had been interviewed by Williamson for the job. And he was employed by the Research Council. And every week, he would come to one of the 4 universities involved. Myself, he would go to Birmingham, Warwick, and a technological university called Cranfield. So he saw each of us once a week. And we were driven in order to find a solution to the problem. And to get this technology, this new technology, out and into industry. And at one stage, I went to see the principal of the University of Edinburgh, Vice Chancellor, who was a biologist. And I said, I'm being pressed to put this work over into industry. He said, how can I do it when I'm doing my duties here at the university? He said, well, what does the Research Council say? They said, well, they say they'll fund an industrial fellowship for you with the Royal Society, whereby you could spend 2 days a week in industry, back in industry, 3 days in the university. And the Vice-Chancellor listened to this, and he said, I think you should go and do this. He said, I think this will be to the benefit of the UK. He said, and professionally it will be good for you too. I think you should go and do it, if your wife agrees. And said, behind every great man there's usually an even greater woman, or vice versa. But So that was pushed through, and I commuted to this small company, a spin-off company from a university, where we pushed the technology through and we got it into practice. And again, back to this problem, that's what you're going to be faced with when you graduate. Some problem and pushing it through and putting it into practice. This wasn't the end of Williamson's contributions. He was invited to join something called the National Economic Development Council. This was a body where industry, exports and imports into the United Kingdom. And he saw this very alarming graph where he saw that exports were actually okay. Now, in a country, Dubai is exactly the same as the UK. The amount you actually sell has to be more than the money that you bring in. And if that goes into reverse, if you're importing more than you're exporting, paying more for the money that you're actually earning, you're actually going into savage decline. And Williamson saw this, and he despaired as to what was going to go on. And then there was a lucky break. Oil was discovered in the UK, off the North Sea. And at the time, I lived in Aberdeen, in a town called Dyson. And I remember actually the Queen coming, and she pressed the button where oil started to flow in the UK. And that actually saved the economy in the UK. Saved the economy. And just as no, actually, and that's again why oil and gas here in Dubai is so important to you. And that changes the whole vision. Changes the whole vision. And there's the Queen. And look at that. Right up to here, right up to 2000, okay, with a dip here, that was what the UK was dependent on in terms of trade balance, where we were self-sufficient in oil and gas, just as Dubai is self-sufficient in oil and gas. And that's where the jobs are. That's where the jobs are. And that's why you need systems engineering. I'll talk in a wee moment or two just about this. Wow, look at this. More problems ahead. But because of that, Williamson wasn't directly involved, but the UK government set up what's called the Marine Technology Directorate. The UK had no experience at all of how to extract oil from underneath the seabed. Absolutely no expertise at all. And they took somebody from BP called Mike Airy, who was an engineering manager. And he was appointed the director of the Marine Technology Directorate. And that was funded by the same research council. And Airy made his way all around the major universities in the UK. And he said, I'm looking for people who can help me to get this oil out from under the North Sea. And he said, and I don't care what your expertise is, but I need your help. And my boss, who was the head of the department and the principal of the university, looked at the people in engineering who they thought could contribute. And we were brought in again in order to contribute our expertise, no matter what it was, to this effort. So what was my expertise in all this? I don't know. All I knew was about how to cut metal or make molds and dies by this time. And here was the extent of the problem. This was, up to that time, the only people who had real expertise in drilling underwater were the Americans. And they were drilling in the Gulf of Mexico, where the water was warm for a start, and it was only a few feet. And all they needed was drill down, and it was dead comfy. in the North Sea, when we were talking about the weather, when I left Edinburgh on Sunday, the temperature was 12 degrees C. You know, in the North Sea, freezing, and you're drilling like this, and these people want to get the water. They want to get oil out from underneath here. And look, see how far it's going down. So, as always, back to the drawing board. Think, think, think. Use your head. Use your head. This guy, Mike 80, yeah, interviewed me. What can you do? I thought, well, all this process I'm working on, it uses aqueous salt water. Well, why can't you use salt water? And this sort of opened up yet another. And I said, well, do these people need to use cutting technology underwater? Too true they do. Too true they do. So my expertise was drawn in again in order to use what I do, but also use my head in order to find some kind of solution. And on we went. And here you are, using grinding, and again, these oil rigs being stuck underwater. And under the North Sea, they move, they're subjected to extremes of difference in temperature, and they crack. And the metallurgists were saying they needed some way to stop fatigue cracks. And between the old firm that I'd worked for in Newcastle upon Tyne and myself at university, we devised a method of stopping fatigue cracks. And it's done, and I'm not a metallurgist, but stopping fatigue cracks by simply drilling holes in the steel and doing it underwater, several hundred feet underwater, and doing it by remote control using robots. Moreover, they come back saying the metallurgists, they want to check to see what is the metallurgical condition of these metals. Could you guys find out some way to do it? Back to the drawing board again. And again, you don't need big groups, small groups of people. These kind of problems, they're never solved by committees. 2 or 3 people, usually thinking differently, put together your ideas and thrash them out. And there you are. And it's taking this kind of work from a research-based university like yours and putting it into practice. And exactly the same here. Here was British Gas, and they took and they came and they saw what we were doing, and they put into an offshore platform, a place called Morecambe Bay, quite near to Manchester. And they engineered the whole thing, and they took what we were able to do in a laboratory, put it into practice. And in some ways, to me as an engineer, that is arguably probably one of the most satisfying things that you could actually see, where what you've done, you're seeing using your brain, and then design, and then taking it forward and seeing it going into practice. Just like Neil Armstrong, his aeronautical engineering and his experience with the aircraft, with the Air Force, and then stepping onto the moon. Or Williamson himself, all the things that he did. Believe it or not, Williamson was then given one final task. He was told that there were not enough engineers, graduate engineers, going into industry. And he said, well, what do you want me to do? Because he was now, and they said, well, can you come up with some plan? His plan was the analogy of the teaching hospital, of a teaching company, where he would take graduate engineers just when they'd graduated, and they would work for a year or 2 years in a company, and the company would pay something, usually 30% of the salary, and the government would pay 70%, and the graduate engineer would work on a specified program for 2 years or 3 years and be registered for a higher degree and get a degree from the university where he was doing that. And that has been arguably the most successful program that I've known of transferring graduate engineer expertise in a university into industry. And it still exists today. It's now called, it became known as the Knowledge Transfer Scheme. And I had the privilege, again, it wasn't the kind of things I was working on, but I told you about the offshore work. Some of the feedback coming back from companies was concerned with the fact that they wanted something that's a bit faster. So in conjunction with a small company in Newcastle, we worked on what's called water jet cutting. It was a very fast train of water, and we were able to slice through steel underwater at magnitudes of speed that were totally unknown. And it really was fantastic, just the speed. And that is now used widespread. And if it's not used here, I'd be very surprised. But there was an interesting development to it. When I come back to Edinburgh, I was saying earlier, medicine is one of the biggest faculties. I was telling one of my surgeon friends, and he said, could we not use this for cutting and surgery? Because their big problem is infection. I said, well, we could try. So we got a bit of bone, and we tried it out. And this is just an early example. And we used a bit of bone, and we showed that we could use the same technique, narrow it down, make it much more user-friendly, where the surgeons could now use water jet in a form for cutting through bone. And the university press office in Edinburgh, they heard about this work going on. Would you care to see this too? They heard about this work that was going on, and they said, I think we'll do a press release about this. So they did a press about what we'd done, taken technology that we developed for the North Sea and built it in where the surgeons were using it for slicing through bone. And they put out this press release, and I got a phone call from the main newspaper in Glasgow, which is another big city in Scotland, called the Glasgow Herald, the Herald. So the reporter phoned up, and she said, could I get some more information to you about this work? So I talked a bit more about it, so that's very interesting. She said, but you don't have an Edinburgh accent. It's kind of very kind of posh accent in Edinburgh. I said, no, I don't have an Edinburgh accent. So, are you not an Edinburgh graduate? I said, no. I said, well, where did you get your engineering degree? I said, I got it from Glasgow University. And she said, and you're now a professor at Edinburgh University? I said, yes, that's right. She said, oh, you really have done well, haven't you? Here we are. So what are the problems? What are the problems that we are now facing as we come into the 15 years into the 21st century? Where are we going? Where are you going? Where are we going to get the energy from? Yeah, you can get oil in Dubai. You used to be able to get oil in the UK, but it's going down. You can get gas. We had coal. Before I came here, as of Qatar's actually got coal reserves. I don't know if you knew that, but you have. Can you go to biomass? Huge debate in the UK about nuclear. Scotland won't have it. England, within the United Kingdom, they're going to build them in England, but they're not going to get them in Scotland. Or do you go to the renewables? And look at this. Yeah, we've got plenty, as I know to personal experience, lots of wind and tidal, wave, solar. It's interesting. From time to time, I am asked to vet research grant applications from the Middle East. And I would say 90% of them deal with research into solar. And your beautiful sun here, and why not use it? So, what's your contribution going to be? Are you going to become involved in further explanation to get more and more oil? Or is it going to be gas? Is your boss going to come to you and say, there's some problem here, and I want you to solve it because you're the best. You've come from you've got a good postgraduate qualification. Can you solve it? Coal? Wow, well, coal is actually, we don't have much coal left, but could it be coal? Some countries in the Far East, coal is still the mainstay. Is it going to be clean coal? Is it dirty coal? How are you going to get it out? Certainly not the way that it was done years and years ago, which really was a filthy, dangerous occupation. And here we are. Or, here in Dubai, should there be more, and I don't know the answer to that, I'm asking you the question, could it be solar energy? Could that be the part of the solution internationally, or here in Dubai? Or, not so much here, but it's interesting, several years ago I was at a meeting in London where they were talking, some of the government officials, and they had a bunch of us engineers together. And they said, and the government officials, the civil service said, well, you people, you engineers, you find the solution. And one of the solutions that's being advocated is fracking. And the critics of it are saying that the environmental effect of fracking is actually enormous. And believe it or not, where there were old coal fields, there is where fracking can be found. Between the two main cities in Scotland, between Edinburgh and Glasgow, the whole area is all coal workings. And that's been identified as an area where fracking could economically be beneficial, could be done. And the uproar that's going to follow is actually where the debates, the environmentalists will be saying, we don't want it, and the economists are going to say, well, you might not want it, but you actually need it. These are the kind of debates where, and again, that's a solution that was unforeseen even just over 10 years ago. And I'll say, you as the engineers of the future, that's the kind of problem that you're going to be faced with, of being asked these questions to find a solution. Find a solution. And not only, it's not just a question of finding the energy, it's also a question of taking that energy and putting it into different types of form. And here is a scientist called Michael Faraday. And I must say, much of my own researches owed much to this man who had lived around about 1830. He was the one who discovered the laws of electrolysis. And it was he who did pioneering work. Again, innovative work of realizing that you could convert energy into mechanical forms, electrical forms, chemical forms, and you could make them pass from one to the other. The Prime Minister of the day in the UK was called Gladstone. And Gladstone had heard about this man working on energy at a place called the Royal Institution in London, which still exists today. And so Gladstone, the Prime Minister, came to see Michael Faraday, and Michael Faraday demonstrated to the Prime Minister electricity. And when Gladstone saw it, he said to Faraday, well, what good will electricity do? And Faraday said to him, well, Prime Minister, at the present stage, we don't know, but all I can tell you is when we find a use, which we will, you'll find out how to tax it. But look at these things. Here's Faraday, success. Concentration, in other words, keep your eye on the ball, stay focused. Okay? Discriminate, in other words, separate out what you need to do from what you don't need to do. Get yourself organized. Faraday wrote down every piece of information in notebooks. Wrote everything down that he was doing. And probably more so than anybody, he knew how to innovate, to find the solution to a problem where no solution existed beforehand. And there you are, and back to Robert Louis Stevenson, he learned how to communicate. He kept his notebooks where everything was noted down that he had done, and then he published the work. And Faraday published something like 400 papers based on the work that he had done. It was all written down. And Professor Whalley and I were just talking this afternoon about he and I publish in Proceedings of the Institution of Mechanical Engineers, where we write down the work. And yesterday we were talking about some of the dissertations that you do or will do in connection with your work, where that work can be taken out and published in journals, where it is then a demonstration of what you've been able to do in terms of your creativity and your innovation. So here we are. This is what we're able to do with all this energy. Okay, we can convert it. And here you can oops, daisy. Here's your chemical energy, which Faraday worked on, and you can convert it into electricity, or you can take your chemical energy from your battery, and you can make it to run your motor car. You can take your electricity, and you can make it fire up the light bulbs that are in this room. You can do what Neil Armstrong done. You can use your energy and you can launch a rocket to take you to the moon. Or here, even food in terms of even the pizza or whatever you have, your pizza margherita or your lasagna or whatever. The energy that you get from food can then give you the energy that you need to come here tonight to listen to a lecture or to compete in athletics or take part in the Commonwealth, in the Olympic Games. Or even when you go home tonight, watching television, or even the energy that's used to provide this microphone to me. And all that comes from the energy that you're studying and the systems engineering that's so important to it. Unfortunately, somebody once said to me, you get nothing for nothing in this life, and it's very true, but energy has its undesirable effects too. And here are some of us that face us in the 21st century. Climate change, carbon dioxide and methane, and the pollution of air and water, and the harm itself to human health. And talking about Paul Dirac and his quantum mechanics and his Nobel Prize and the nanotechnology that's come from that. As you know yourself, the danger that can come from nanoparticles, breathing in, and the effects that can have on the lung, are some of the very undesirable parts of nanotechnology. And Dirac would have been horrified. Dirac would have been horrified if known that there were undesirable parts of quantum mechanics as well, or the nanotechnology that followed on from it. And that's your responsibility too. Someday I will come to you and say, we've got these problems. Can you find a solution to them? And here you are. The aeroplane that I came here on Sunday, there's the vapor trails. The motor car that you might or might not have used to get here, the emissions from that. Or the factories, especially, I regret to say, in the UK, in Europe, in the Far East, Yeah, turning out products far cheaper than anybody else can, but the pollution that can cause is a danger to human health. And you're going to have to find the solution to it. Or can you travel by bike? And I know at Edinburgh University, every year, some of us apply for car parking permits, and then you get this form to fill in to say, is there any other form of transport to get to where you are? And you went to me, can you walk there? Can you travel by bike? Or whatever, in order to. And then you're given a score. How far are you away? You have lectures at night, lectures through the day, this, that. And they give you a point system. And then reluctantly, they might or might not give you a car parking permit. And there's climate change. Wow, flooding. Even in Scotland, with our climate, the effects of flooding caused by climate change are being noticed. And flooding. Here is people trying to find a solution to carbon capture, and there's a big unit at Edinburgh University trying to find new methods of capturing carbon. And you yourselves, I'm sure, will be asked to find innovative methods of capturing the carbon or reducing carbon emission. And there you are. So there's the challenges for energy. That's what you've got to do. Yeah, we've got to discover it, find new methods, we've got to use it, we've got to find the effects. And your studies here, though, it's the combination of going from one engineering discipline to another. And this capacity, and the fact that you've had the entrance qualifications to come here, means that you have the capacity in order to cross these disciplinary boundaries in engineering in order to find the solution. And that's why systems engineering, to me, is actually so important. In energy, yeah, you've got to find it, you've got to process it, refine it, and then you've got to generate power. And again, back to old friend Williamson, within your course here, you're given modern computing methods in order to do the simulation that's needed in order to help more quickly to find these solutions. And that's why engineering is the future for you and for me. And finally, that's why too, the far-sighted ruler in Dubai realized that the future of his country lies with young people like you coming to university. And also he realized that one way is to get the benefit of other people in other countries. Here, in terms of the big universities in Edinburgh, founded more than 400 years ago. Manchester, and interesting enough, there was somebody else who studied engineering who got the Nobel Prize, called Rutherford. And he studied engineering. And he was the man who split the atom. So that background, the kind of training that engineering is given. In Cardiff, again, one of the major universities. I've been to Cardiff and I've seen the really fantastic facilities that they've got there. Interesting. 4 countries that make up the UK. And this university has joined with them. And education, higher education, is the legacy. And that's why you find us as partners that want to see your country develop and contribute what we've learned in order to make Dubai really such a great country. And the big engineering institutions are in as well. Institution of Mechanical Engineers, founded more than 100 years ago by the two Stevensons, who built the steam locomotive and sent his son to study engineering at Edinburgh to discover there wasn't any engineering there at the time. And the engineering and technology, taking electrical engineering and manufacturing engineering, putting it in. And they're the two big engineering players. Just as our degrees are monitored by them, your degrees too. And that's why that kind of charter actually is so important. where there's the international hallmark to make sure that your engineering degree is recognised. And let me say, first of all, it's called the British University in Dubai. Do you know why I think it should be called? I think it should be called the best university in Dubai. Thank you. Joe? Mm-hmm.
Okay, Professor Wickham, we'll take questions if anyone has any. Did the audience know that in UK, in the north of England alone, there's enough gas from fracking to last 200 years?
There we are.
Maybe we go to Scotland, it's even more.
Well, there we are. But there you are. That's a solution that was unthought of. But it is a solution. It is a solution. Mm-hmm. Well, need to overcome the environmental problems, but yeah. Well, that's right. Well, it's interesting you say that. When I before I went to Edinburgh University, I'd gone from industry back into university in Aberdeen, and there, when oil was discovered in the North Sea, the airport used to close at 10 o'clock at night. And then because of helicopters flying in and out of the rigs, the city council, they had to approve a request by the big oil companies to open up the airport at night. Of course, all the inhabitants, they protested because they said, we're not going to get any sleep. But it's true. Well, people say, well, what do you want? Do you want the oil to come afloat, and do you want these people being flown in and out by the helicopters? So there was a compromise, and I think they now close at 10 o'clock, 12 o'clock at night. But environmental, what do you want? But in terms of fracking, it's interesting, down in the kind of south-east of England, looking at the kind of map of the UK, reserves have been discovered there where fracking will be the solution. Fracking will be the solution. And they're already having these debates as to whether the environmental effects. But, I've been to lectures where this environmental effect is actually being played down because it's not as serious, but kind of a bit emotional. No, it's not really as serious. Mind you, I'll probably be slaughtered as soon as I said that. But basically, the environmental effects are not as great.
You mentioned nuclear energy, and you said it's still controversial, which it is.
Yeah.
Do you think that's the failing of engineers to address the problems, or the failing of engineers or others to communicate the answers to the problems?
Good question. I don't think it's been the fault of the engineers to address the problem. It's also debatable. It's interesting. Between the countries in the UK, the Scottish government will not have nuclear because of the claimed effects of radiation. Whereas the government in Westminster, with control over England and Wales and Northern Ireland, they're quite happy for nuclear power stations to go ahead. And if you look to continental Europe, France they have built a number of nuclear power stations in order to provide France with the energy that it needs. But again, the effects of that type of radiation, 25 years, I think part of the problem is actually fear of a nuclear explosion, such as happened in Chernobyl and also in Japan. So therefore, to me, the solution is the safety measures. The safety measures that need to be put in, and that's a place where the engineers really have to play their part. And I think it's the safety that really has to be looked at. Safety engineering has to be looked at. rather than communication. I don't think the communication is a problem. The trouble with often engineers, actually, they're not politicians. You know, and they'll often kind of speak their mind rather than, you know, couch it in the kind of language that a politician expects to hear. And everybody blames the politicians, and why shouldn't I? So therefore, the engineers will give them the message. But there, it's up to the politicians to decide whether they're prepared to implement what is needed. I'll give you an example of that, actually. The firm that I used to work for in Newcastle, the chairman was called, he was a metallurgist called Monty Finiston. He was the managing director and then became the chairman of the company that I worked for. And then he went to what then was called British Steel, where he became the chairman. And he told the government of the day that the steel industry in the UK was uncompetitive. And what did the government do? They fired him. But he told them the facts. Steel coming in from other countries was actually cheaper than he was able to produce. And I regret to say, a lot of these things, communication, yeah, I think that's actually so important. That's why actually, again, I noticed the other day, there were just in the corridor, there was a sign up about presentations. And I think actually for you as doing your course here, you know, these opportunities that you get actually to present your work actually are so important at your stage. And again, in Edinburgh, we start them off. They stand up for these I say are you know, undergraduate level. First of all, getting they stand up even for 2 minutes. Some of them are absolutely terrified. But speaking in public, 2 minutes. And then the next time we come on, next time we get them to speak for 5 minutes. And then later, and then they're doing 15 minutes. But the capacity to present your work is a skill, but it's also part of your university education in order to go and present your work. And give you another example of that. Have I got time, Bob? Maybe not. So some time ago, at the time, his name was David King. He became the scientific advisor to the British government. And Tony Blair was the Prime Minister at the time. And it was the time of, there was a disease, foot and mouth disease in the UK. It was the disease, and it was killing, you know, they were slaughtering cattle. And King got a message to say that the Prime Minister was going to speak to Parliament about what the country was going to do about it. And could King come and brief him? And King said, he said, the Prime Minister he'll give you 20 minutes. And during that time, King said he was frantic, and all these kind of research assistants helping him to put together a talk. I mean, the Prime Minister was not an engineer, not a scientist. And King had to put this information to him in such a way that Blair could take in the information and then assimilate it in such a way that when he spoke to the Parliament, and these people were then voting on what his country was going to do, that this information had to be presented. King said it was the most awful thing to do, you know, kind of boil down this information. But the questions asked there, that's where communication and how you present your work is actually important. And that's why these dissertations that you do actually are so important as well.
Okay, well, thank you very much. I'd like to present Professor McGeoch with this small memento from the university in recognition of his excellent lecture this evening. Joe, I hope you'll receive this from me with all my best wishes, all our best wishes, and good wishes to you for a safe journey home.
Thank you very much indeed.
And in answer to your question, nuclear power is inherently unstable. If the control rods are not in there, it's going to explode, I promise you. Thank you very much.
All right, thank you very much. Well, thanks very much. Gosh, I'll treasure this. That's
I
very.
think it's just a
it's lovely.
paperweight or something. In
Well, it's lovely, but anyway, it's a real memento. So.
Okay, good. Anyway, you do that.
Thank you very much.
I hope it's not a human one.
No, it's not a human one. No, wouldn't be allowed. All right, okay, I'll let you.